Hey guys, welcome to this session by Intellipaat and also welcome to the day 7 of the Python week. So, in this session, we're going to learn various Python concepts again. Now, before moving on to this session, let's take a quick glance at the agenda. So, we'll first understand how to use a thread pool. Once we understand that, we'll be looking into an actual demo on using thread pool executor. Once that is done, we'll be looking into concepts like race conditions, and once that is done, again we'll do a hands-on demo on race conditions, and finally we'll be looking into synchronization using locks. So this is a continuation of the previous session.
So before moving on with the session, please subscribe to our channel.
And also hit the bell icon for the upcoming updates from our channel. And also, if you enjoy our content, you can leave a like.
Alright guys, now let's take a look at thread pool executor. We've taken a look at how we can use multiple threads manually. However, thread pool executor is a much better alternative. It allows us to abstract away the nitty-gritty details that we need to take care of when we're working with threads, and allows us to create a pool of threads from which new threads can be extracted and tasks can be performed in that thread pool. So although, as you can see, we described that there are methods which you can use to use a list of threads and managing all the threads and their interactions manually. Now this is doable, you can do this, but it is really cumbersome. And if you are working with a large number of threads, let's say anywhere around 4, 5, 7, 8 threads, then it could get really ugly to just write the code to create a new thread, submit a function, to call the start method, call the join method on the appropriate time, make sure that all the data is in sync, and then perform all the other tasks that need to be performed. So in Python, there is an easier way to get started to start and manage the thread, manage a group of threads together. It is called thread pool executor. Now, if you come from other languages such as Java or other languages like C++, there are similar concepts available as well. In Java, I believe it is called a thread pool executor, but there are more specific types of it, like cached thread pool executor, fixed thread pool executor, so on and so forth. But the main objective of these classes is the same. So in Python, thread pool executor is part of the standard library in the concurrent.futures package. So in this package, you can import the thread pool executor, and from there on, you can start creating a thread pool, submitting tasks to the thread pool. The thread pool will then use one of the threads that it has already created for you to essentially run the task in the background, and when the task is done, you can extract the result out of it. The correct way of using thread pool executor is to use it inside a with block. If you've ever used any thing called context managers, essentially a with block takes some values and then calls the appropriate methods on it in order to create a life cycle. So for instance, if you've ever worked with a file, you have to create the file using the open method, and then at the end of the day, you have to remember to close the file using the close method. Using context managers, you can forget about doing that. You can just focus on the task that you need to perform. All you have to do is use the with keyword, and inside the block that is created with that, write all the code that is related to the file. Once the code is executed, the indent out of that block, and at the end of the block, the file will be closed and all the resources will be freed automatically. So you don't have to worry about that at all. That's the with statement, also called the context manager, and you can use it with thread pools as well. So this is so that when the block is over, we are done using the thread pool and it can free up resources automatically. Since thread pools create multiple threads, it may end up acquiring multiple resources, which may or may not be something that you want. So just make sure that you are freeing up resources as you go along, because if you don't, then this could cause memory leaks and a lot of erratic behavior in your application. So when instantiating a thread pool executor, all we need is a specific keyworded argument called max workers. Max underscore workers is the keyworded argument, and this needs to be set to the maximum number of threads that you want it to be able to create. Don't set the number too low or your application will falter. Don't set it too high or your resources will start making your entire operating system work slow, because you are creating like 50, 60 threads and that are not needed. Mainly it is a work of experimentation. Sometimes you know how many threads you need, sometimes you need to experiment with it and land up on a number that works for you in the long run. Just make sure that the number is not too huge and not too small either. And then from there on, we use the map function. Inside the map function, it will take a function that will be used to step through multiple threads and iterable of things, passing each one of the thread in the pool. So basically, you just use the map function, pass in some function that will be run on multiple threads, and that will be done automatically. This may be a little difficult for you to understand right now, but that's okay because threads are a little complicated of a topic. Threads also are very powerful. So let's take a look at how we can use thread pools in a hands-on, and then we'll figure out what are the problems with threads using race conditions. Alright guys, now let's take a look at how you can use thread pool executor. So we'll use the same function that we had earlier. I have imported concurrent.futures right now. You can choose to not import it or import it somewhere else. I'll just choose from concurrent.futures, import thread pool executor. Now all I have to do is use it inside a with block. So I'll just use thread pool executor, pass in max workers to be 3 as executor, and now I'll use executor dot map. I'll pass in the thread function that I want to use, and I will pass in a range. Range is going to be of 3. Now if I go back, run this code, 3 threads get started and the 3 threads end. You can see that the threads are not necessarily in the same order as they started in. So again, this happens every time we run it. As you can see right now, the second thread has ended, then the first thread has ended, and the third thread has ended. So you can't really determine how the functions are going to be called. However, this is what the output is going to be like. So what's happening is we are creating 3 threads and then we are mapping them on the thread function. Now this is just one way of doing it. Let me show you another way. Executor dot submit, and this will work the same way. So I'll just pass in target is equals to thread function args is equals to 0. I believe that's the syntax. Let me just check. Okay. Submit expected at least one positional argument, got 0. Okay. So if I were to do it this way now, so thread 0 starts and then thread 0 ends. And that's basically it. So that's how threads work. Now if I want to create these many threads, 1, 2, 3, 4, 5, and now if I run this here, 3 threads start, then they end, and then more threads are started, and as soon as they are done, they end. So as you can see, I have created 3 threads, and now as soon as the threads get freed up, new tasks are added. So 3 threads start, one of the thread ends, another thread starts, 2 threads end, 2 threads start, 1 thread ends, 1 thread starts, and then all the threads that were remaining, which is 4, 5, 6, end exactly at the same time, and we get the output. So this is what the usefulness of thread pool executor is. You can create and manage threads automatically, and as you can see, I didn't have to write the join method. So for instance, if I were to now print done, now the main thread will wait until everything is finished and we're done. So instead of me having to call join automatically on all of these functions one by one, thread pool executor does it for me. So that's how this works. Now let's see what else we can learn. Race conditions. Race conditions are problems that we could face when we're using multiple threads. So although threading is a very useful concept, it has several challenges associated with it, which is why many beginners are not advised to use threads until they are absolutely necessary. Now threads are very useful. They provide a lot of power. However, that power needs to be taken into context with the problems that you might face when you are working with threads. To give you a quick example, let's say that you are working with multiple threads. There could be problems leading to data corruption. There could be problems leading to managing multiple threads. It's just a lot of problems all around. So we need to be able to take care of that. One of the several challenges is called race conditions. Race conditions are some of the most prevalent challenges that comes when dealing with threads, mainly because when we're using threads, we are using multiple flows of executions that are competing to work, that are competing for resources and working as fast as possible. There are other problems with threads as well. However, this is the most problematic and the most sneaky one. A race condition is a situation where we get incorrect results because multiple threads are manipulating the same data or the resource. Let's say we have some data in the memory and multiple threads gain access to it and are changing it continuously. That could lead to a lot of issues. And since these multiple threads are first accessing and then manipulating the data all at once, it is possible that they end up manipulating some old data while another thread is already updated the data in memory. It could be a little difficult to wrap your head around this concept, but basically, if two threads are simultaneously processing the same amount of data, let's say that in memory we have some data and first thread gets access to it to update it, the second thread gets access to it to manipulate it as well. The first thread updates it, second thread updates it, first thread puts the data back into the memory, and the second thread overrides that data by putting the new data back into the memory. Now, the thread that should have been updated twice has already been updated once. To give you a better example, let's take a look at an example for now. For example, consider two threads trying to increment a value of a counter variable that is initially set to 0. We have memories and two threads. The value in the memory is currently 0, and both the threads, thread 1 and thread 2, will execute the same amount of code in which they will read the memory value, which will be 0, and substitute it for a value that is adding 1 to the current value in memory. So it's 0, 0 plus 1 would be 1. However, both the threads will be doing it separately. So the first thread gains access to the memory, reads it into the variable, determines that the value is currently 0 and we need to update it to be 1. While it's doing that, the second thread gains access to the same memory and at the same time accesses it and adds 1 to it as well. So now both the threads have the value 1 and they both put the value one after the other. Now, the problem here is that the value should be 2. Since two threads have accessed and incremented the counter, the count should be 2. However, the count is 1. This may not always happen, but it happens frequently enough to disrupt the entire flow of execution. So, for instance, if you have multiple threads working simultaneously, it may be that one thread ends up waiting for another thread based on how the schedule is happening, but not all the time. Sometimes it may end up stepping on some other thread's toes and updating the data incorrectly and getting incorrect results. So now the value instead of being 2 is 1 because both the threads did not wait for each other to finish. This is a very critical problem, especially in applications that need high response times and high throughput times. You can lead to data corruptions. If you're creating a database and this is the kind of way you deal with race conditions, then your database will end up creating incorrect values in databases. Updating data is going to take a lot of time and a lot of hassle, and it's going to be really problematic. So to overcome this, there are certain ways. Let's take a look at one of those.
Just a quick info, guys. Intellipaat provides online Python certification training mentored by industry experts, the course link of which is given in the description below. Now, let's continue with the session.
Alright guys, now let's take a look at race condition. So this is what the code we had earlier was. I'll make a few changes here. Instead of this, I'll create a class. I'll call it counter. It will have
Just a quick info, guys. Test your knowledge of Python by answering this question. How many CPUs will the threading library use? A. 0, B. 1, C. 2, D. All available CPUs. Comment your answer in the comment section below. Subscribe to Intellipaat to know the right answer. Now, let's continue with the session.
an init function, and I will just initialize a property of value to be 0. Then I'll create an update function. I will take in a parameter of let's say name, and all this is going to do is it's going to create Firstly, we're going to print it. So update started on thread name, and then the update has ended on thread 1 as well. Now here we're going to make some updates. Before that, let's just take a look at how we're going to do it. So I'm going to take a copy of value in val, so self dot value. Now value plus equals 1. So I'm getting the value, I'm updating it. So now the value is 1 more than what it previously was. Now I'm going to sleep for 0.1 seconds. It could be more as well, but 0.1 generally works. And now I'm just going to update self dot value is equals to 1. So now what's going to happen is, imagine this is a memory address. I reach into the memory address, pull out the version of data that I want, update it, sleep for a second, wait for a second, and then I will put the new updated data back into it. So update is now ended. Now here I have this. Instead of doing it this way, what I will do is I'll create a for index in range 2. So I'm going to create two threads, and what I'm going to do is I'm going to create a counter. This is done, and I want to call the update function, and I will pass in the index, and then at the end I will print done. So now if I were to run this, as you can see, it is showing me that it's done immediately. Let's see why that is. We have a counter function, we have an update function, we pass in self name, and I've saved it, and I create a counter variable. The name is passed in. We print the thread's name. Let me just increase it to be 1 second. Let's see if printing is the problem. So if I run this, it's printing done again. We create a counter using the max thread pool. I'll just use 2 threads instead of 3. So it is 2 now. Now we have an index in the range of 2, which corresponds with our max number of workers. And we use executor.submit. We pass in the counter.update function, and we pass in the value. Let's finally, instead of doing this, I'll print counter.value. Go back, update, and right now it's 0. It may be that we are not getting the value, so let me just see counter.update, and I'll pass in 1 here. If I run this, as you can see, update start can only concat. Oh, okay, fine. So we are running into an error. This is also something that you should take care of. Whenever you run into an error like this and you're not getting an output in thread executor, it's because in thread executor, the exceptions are suppressed so that the normal flow of execution doesn't get interrupted. Now if I run this, now the problem here is that I am using 2 threads, thread 0 and thread 1. The issue is that it is updating only once. So the value was supposed to be 2, but now it's 1. If I were to remove the sleep function, and if I go back, and if I run this, as you can see that the thread is 0, thread 0 starts, thread 1 starts. Both of them updated and then move on, and now we have the value of 2. But if I sleep, let's say that this is a network problem, I'm using internet to update it, it's on a server, then that takes some time. If I run this again, I'm getting the incorrect value. So this is a race condition because the correct value is not getting updated and we are running into some errors. To overcome this error, what we can do is we can use certain properties called locks. Let's take a look at that. Alright guys, now let's take a look at how you can use synchronization using clocks. So in synchronization using locks, we'll take a look at locks and how we can prevent race conditions using locks in Python. So there are a number of ways of solving race conditions in Python. One of the easiest ways is to make use of locks. If you've ever come across something called a lock in threading, then this is what we'll be discussing here as well. Locks allow you to avoid race conditions and allowing only one thread at a time into the read, modify, write section of your code. So if, for instance, If you have three threads trying to access some value in memory and modify it, not just read it, but read it and then modify it and then again update it. In cases like this, what we'll try to do is we will make sure that only one thread gets access to that memory location at a time. If it's just about processing, then multiple threads can access it. Just read the data and process it, and then put it somewhere else.
Just a quick info, guys. Intellipaat provides online Python certification training mentored by industry experts, the course link of which is given in the description below. Now, let's continue with the session.
But if it's not about processing and it is about updating some values, then locks are essential. In some other languages, a similar idea is called mutex, which is based on the idea of mutual exclusion, which is what locks do as well. So if you've ever come across Java has the idea of mutex. The same concept applies here as well, so we use mutex here. A lock is an object that acts like a pass or a token which allows only one thread at a time to have access to it. Think of it this way. Once the threads want to gain access to a particular resource, they end up in a queue, and each thread at the beginning of the queue is given a token or a pass. That pass means that the thread can enter the memory location and then update the value and then leave. As soon as it leaves, the next thread that's waiting gets the token, and the current thread leaves the token, and the next thread gets that token and then goes in and does the task. So it's sequential. However, it's multiple threads waiting for in a sequence in order to get the task done. Now, any other thread that wants access to the same lock must wait until the current owner of the lock gives it up. This is essentially what has made locks so useful, because they make other threads wait. So if any other threads want the access, then they have to wait for the current thread to give it up. If no other thread is holding the access to the lock, then the thread that's waiting for it gets the lock. Now, for locks in Python, you would have to lock class from threading package. So you take threading package and you use the lock class from that to create an instance. We can manually create the lock object by simply instantiating the object with the lock class. You don't have to create any other any other. You don't have to pass in any other arguments. Then we can use then we can call the acquire methods to get access to the lock. And as soon as the thread is done, it can call the release method on the lock to release the access to that lock. Now, to do it more succinctly, we can use a context manager, or we can use the lock using the with keyword, so that the Python code can understand how to acquire the lock and how to release the lock, and can call all the methods uh, automatically without us having to manually call the methods at the beginning of the code and at the end of the code. That makes the code a little more readable and a little more succinct, and makes it easier to work with as well. So with that, now let's take a look at how we can use locks inside Python to synchronize race conditions. Alright guys, now let's take a look at how we can prevent race conditions using locks. So in Python, to use locks, all we have to do is, let me just show you the problem right now. We have the code, I run it, and the update should start and end. However, we are running into this issue. So we have some code in which we are updating the values, but we're sleeping for 0.1 second to simulate some threading issues. Let's say that it was network and we are trying to update some value in a database row, and that takes 100 milliseconds. Now we are running into an error in which we are getting inconsistent data. In order to solve this, we'll have to use locks. I'll just import the lock from the threading module. Then I'll create a class property of lock. Now the lock is created. Now all I have to do is I use with self dot underscore lock, and that's about it. So now if I go back, rerun the code, as you can see, the update is 2. No matter how many times I run it, the answer is going to be the same. So what's happening is I run the code and the lock gets acquired. If I want to do it manually without the with statement, then all I would have to do is self.lock.acquire and then call self.lock.release, and yeah, release. it works the same way. However, using it within a with block ensures that I don't have to type these methods and it works the way I expect it. So what's happening now is this. Let's go from the start. We declare a class, we create a counter variable of the class, we create a thread pool executor with maximum of 2 threads. We create 2 threads by submitting the task here. And here I have used counter.update and I passed in the index as the variables. Now this thread gets executed, and since it's inside a thread pool executor, I don't have to use the word join. I don't have to use the join method to allow it to wait for the threads to execute. Goes up. Now inside the update method, I create the update started string. Then I acquire the lock. That means all the other threads will now have to wait. I get the value, update it, simulate 100 milliseconds delay, update the value. Then I will end the thread. As the thread ends, the other thread gets the lock and then it prints it and ends that thread as well. Another thing I can do is, let me just show you. Lock released by thread 1. And instead of it being 100 milliseconds or 0.1 seconds, I'll make it 1 second. Now if I were to run this, and that's it. So what happens is this. Update started on thread 0, lock is acquired by thread 0. Update started on thread 1, now lock is released by thread 0, and then the update has ended on this first thread, which is thread 0. Then the lock gets acquired by thread 1, and then it is released by thread 1. Since no other thread needs the lock, the update ends and we are done with the threading part of the application. So that's how locks work. There's a much more in-depth analysis of threads that you can learn. There are a lot of things about threads ranging from deadlocks, preventing deadlocks, mutual exclusions, principles, and patterns that you can use in order to write multi-threaded code. But that's the end of what we'll be discussing as the basics of threading. So with that, we've come to the end of the module.
Just a quick info, guys. Intellipaat provides online Python certification training mentored by industry experts, the course link of which is given in the description below.
Okay guys, we've come to the end of this session. I hope this session was helpful and informative for you. If you have any queries, leave a comment down below.
Thanks for watching.